If you've been following the rapid evolution of diffusion models, you know that post-training with reinforcement learning has become the standard for aligning generation with human preferences. Methods like Flow-GRPO and Dance-GRPO have shown that online RL can dramatically improve instruction following and visual quality. But there's a fundamental bottleneck that's been hiding in plain sight, especially when it comes to image editing. Current RL pipelines treat an edited image as a single, monolithic outcome. They compute one scalar reward for the entire image, normalize it into a sample-level advantage, and then broadcast that exact same credit signal across every single latent position and diffusion time step. This design relies on what we can call the spatial uniformity assumption. It works fine when you're generating an image from scratch, and the whole thing either looks good or it doesn't. But image editing is inherently spatially non-uniform. You might successfully change a person's shirt color, perfectly preserve the background, but completely botch adding a new object to the foreground. When you collapse all of that into one reward score, the model has no way to distinguish which region succeeded, which region failed, or whether the unedited parts were actually preserved. This is the Spatial Credit Assignment Problem, and it's the main reason why fine-grained, multi-region editing still struggles with current RL post-training. To fix this, the researchers behind SpatialFlow-GRPO introduced a completely different approach: spatially structured credit assignment. Instead of optimizing at the image level, they break the optimization down into semantic regions. The framework starts with a new region-aware reward model called SFReward. Rather than spitting out a single score, SFReward is trained to output structured feedback. It identifies the exact bounding boxes for edited regions, assigns semantic labels to them, and then scores each region independently for semantic consistency and perceptual quality. It also evaluates the background to ensure preservation, and provides an overall image-level perceptual score. This gives the RL loop the spatial resolution it's been missing. But how do you actually turn these structured region scores into a training signal? You can't just plug them directly into a standard GRPO update, because rewards are only comparable within the same instruction and semantic label. So SpatialFlow-GRPO normalizes the region rewards by grouping them across the sampled candidates for a given instruction. For each semantic label, it calculates the mean and standard deviation, then computes a z-score to get the region-level advantage. However, there's a catch. If you only optimize based on these pure local advantages, you risk breaking global composition, identity preservation, or naturalness. The model might over-optimize a small foreground region at the expense of the whole image. To solve this, the framework mixes the region advantage with the global advantage using a dynamic mixing coefficient, alpha. Early in training, alpha is kept low, so the model relies more on the global quality anchor. As training progresses, alpha ramps up using a clipped cosine schedule, gradually shifting the focus toward fine-grained region feedback. This gives the optimizer the best of both worlds: global stability early on and spatial precision later. Now here's where the real technical innovation happens. In standard Flow-GRPO, the policy objective computes a log ratio at every latent position, clips it, and averages it globally. This dilutes local signals because the large background area dominates the gradient. SpatialFlow-GRPO changes the granularity of the update to match the granularity of the reward. First, it aggregates the position-level log ratios within each semantic region before applying the clipping. This creates a region-consistent policy ratio, ensuring that the measure of how much the policy changed has the exact same spatial resolution as the advantage signal. Second, when aggregating the loss across different regions, the framework introduces a power-weighted scheme controlled by a parameter beta. Instead of letting large background regions drown out small foreground edits, beta allows you to tune how much the aggregation leans toward area weighting versus equal region weighting. In practice, a beta of 0.7 preserves area information, while significantly boosting the influence of foreground regions. The final objective still includes the standard KL regularization term to prevent the policy from drifting too far from the reference model. But now the advantage, the ratio, and the loss aggregation all operate at the semantic region level. Of course, this entire pipeline depends on high-quality region annotations. The authors trained SFReward on SFReward 14K, a dataset of over 14,000 editing triplets where expert annotators marked bounding boxes and semantic labels, and a multimodal teacher model generated per region success, preservation, and background scores. To properly evaluate whether this approach actually solves the multi-region problem, they also introduced MultiEditBench. Existing benchmarks mostly measure overall quality, but MultiEditBench specifically diagnoses a model's ability to handle 2, 3, 4, or 5 simultaneous editing targets. It isolates spatial complexity by tracking performance as the number of independent edits increases. The results speak for themselves. When applied to both OmniGen2 and FLUX.2 4B, SpatialFlow-GRPO consistently outperforms the standard Flow-GRPO baseline across standard editing benchmarks. But the real win is on MultiEditBench. As the number of simultaneous edits increases, the gap widens. SpatialFlow-GRPO maintains instruction following and structural integrity, much better than global-only RL. The ablation studies reveal exactly why this works. When you replace the sample-level reward with pure region rewards without any global mixing, performance actually drops. The local signals are too noisy early in training and amplify artifacts. Adding the global region hybrid advantage stabilizes it. Turning on the cosine warmup for alpha prevents early collapse. And enabling the region-balanced aggregation with beta prevents the background from diluting the foreground signal. The takeaway is clear. Fine-grained credit assignment only works when it's carefully coupled with global quality constraints and properly aligned policy updates. SpatialFlow-GRPO represents a necessary shift in how we approach reinforcement learning for image editing. By treating semantic regions as the fundamental unit of optimization, it finally aligns the granularity of the reward signal with the granularity of the editing task. It proves that spatial credit assignment isn't just a nice-to-have, it's essential for complex, multi-target editing. The framework is built on solid theoretical grounding, backed by a dedicated dataset and benchmark, and delivers measurable gains across different diffusion backbones. If you're working on post-training diffusion models, instruction-based editing, or reward shaping, this paper is a must-read. The code and dataset are being released to the community, so you can actually experiment with region-aware RL in your own pipelines. Check out the paper, dive into the implementation details, and let's push fine-grained generative models forward. Thanks for watching, and I'll see you in the next one.